And we're back. Welcome back and happy Tuesday. Today we'll be continuing with our coverage of the application layer with a focus on peer-to-peer networks and content distribution networks. But before we begin, some administrative bits. Project number 2 is out on the course Blackboard. It will be due on Tuesday, February 16th at the usual 11:59 and 59 seconds, 1 second before midnight. So let's take a look at peer-to-peer applications. And so in peer-to-peer architectures, we have no always-on server. Peers are so-called occasionally connected, meaning they can come and go. And arbitrary end systems, these processes, these peers, communicate directly with one another. So these peers are intermittently connected and therefore can change their IP address. And some examples include things like voice over IP like Skype and file distribution BitTorrent, very, very popular. And so the question then, if you've ever used something like BitTorrent, well, you'll find that it is very fast in downloading and distributing files. But why exactly is this? Well, we'll take consideration, and this is in the book, of the difference between client-server and peer-to-peer. So the question underlying the BitTorrent system is how much time it takes to distribute a file, and let's assume that file is some size F in bits, from one server to n peers. So you can imagine this is something like maybe a video that you're trying to stream or some file that you're trying to transfer. And so this idea is you want to distribute it. Everyone gets a copy, and many peers get a copy of this file. And so we know that the bottleneck link is typically the access link for the client or the server. And so peer upload and download capacity is oftentimes the limited resource. And so here in this diagram, we have our server here on the left-hand side, and that server has some storage on which some file of size F resides. And the goal is to get this file to each one of our n many peers. So we have the first peer here, the second peer here, going all around to and including the nth peer down here. And so each peer is associated with an upload and a download access link capacity or bandwidth. And so we have U1 is the upload link capacity. It's the rate at which peer number 1 can upload a file into the network. And likewise, the download capacity, D1, is the rate at which peer 1 can download a file off the network. And so each one of those peers has its upload capacity, U sub I, and the download capacity, D sub I, respectively. And so we'll make the assumption here that the network bandwidth, which is typically the case for the network core, the network bandwidth for the network core is so big that it's negligible, the amount of time it takes for files and for content, for packets to make their way across the network core. All right. And so the question then, what happens when you distribute a file in a client-server scenario? Now, in this scenario, well, the server has to sequentially upload n many copies of that file. So the server uploads the file once for the first client, another time for the second, another time for the third peer, another time for the fourth peer, and so forth, another time for the nth peer. Not clients, but peers. And so the time then for the server to send one copy into the network, we take F and divide by the transmission rate for the access link to upload for the server. So we get F divided by U sub S. And that's the time to send one copy into the network. Now, of course, if you're doing that n many times, that's F upon U sub S plus F upon U sub S added to itself, big N many times. And so to send n many copies, because the server has to send that n times, one for each one of the n peers, that's n times F upon U sub S. And so, in addition, once these files have been uploaded into the network by the server, each machine, each peer, the client part of each peer, must download a copy of the file. And if we're going to look at that download for each one of the clients or client roles on the network, let's define dmin as the download rate or the download transmission rate associated with the slowest client. Okay. And we know that, of course, it doesn't matter what the particular download rates are for the clients. What matters is that there's the slowest one. We'll just identify that as dmin. And so in this particular case, dmin could be D1, it could be D2, it could be DN, and so forth. And so dmin is that particular download rate, DI, associated with the slowest downloading client. And so the download rate for that client that is the slowest, or the one associated with the minimum download rate, it's going to have the largest download time. And that largest download time is going to be F divided by dmin. F because that's the size of the file that's now in the network core, and then dmin because that's the rate of that slowest download link associated with the client's transmission rate. And so then the time it takes to distribute in client-server networks to distribute that file of size F to n many clients is going to be whichever is the maximum between the two. If it's the bottleneck is at the server, well, that's going to be n times F upon US. And if the bottleneck is the slowest downloading client, that's going to be F over dmin. Now, of course, in order to send this file, distribute it to each one of the n many clients, you have to upload it n many times. And of course, we know the task of distributing that file to all of these n many clients is not done until the slowest machine or the machine or client associated with the slowest link for downloading has completed its download. And so it's going to be the download delay or the time for distributing that file using client server D sub CS is going to be at least the greater between these two. It's going to be the server upload or the slowest client download. Okay. And so that's for the client server case. It increases, we'll notice, linearly in n. As you add more and more client instances, we notice that the server's download is going to increase. So let's take a look at distributing a file in the peer-to-peer case. And so with peer-to-peer, we have more than one peer on the network able to distribute this file. So the server is certainly going to upload the file into the network at a time of F divided by U sub S. That hasn't changed. But then each client then must download a file copy, but they can also serve as the source for uploading that file for some other client in the network. And so each of these clients, these peers, can act as if it were a server and upload that file. And so each client has to download a file copy, and the maximum download time for all the clients is going to be whatever the slowest client is. And so we have that F divided by dmin associated with the client that has the smallest bandwidth for its access link, F divided by dmin. But as the clients aggregate, it's the total upload of all the clients that has to satisfy this n times F, which is the n copies of that file of size F many bits. And so the maximum upload rate for this peer-to-peer network is going to consist of the upload of the server plus the aggregation or the sum of all of the upload rates for all of the clients in the network. And so the clients as an aggregate have to download NF bits, but the maximum upload rate is going to increase with the number of clients. And so that's going to be, that max upload rate is going to be U sub S, the upload rate of the server, plus the sum of all of the upload rates or upload transmission rates for each of the clients. And so the time it takes to distribute F to N many clients in this peer-to-peer approach is going to involve bottlenecks from three different sources. One is going to be the server. So here, F upon U sub S, that's going to be the server. The other is going to be the download of the slowest client. So that's the download of the slowest client. And we have the distribution associated with the aggregate ability to upload across the entire peer-to-peer network. So that's NF, which is the total data, and we have in the denominator U sub S, or the server, plus the sum of all the upload rates for all the clients. And this is the peer network upload. Because when the peer network uploads, it's distributing those N copies of that file of size F. And so this is going to be the aggregate rate, or time rather, for the peer-to-peer network to distribute this file for all of the N many peers that need it. And so the time it takes to distribute this file to N many clients in the peer-to-peer approach is going to be whichever of these terms, at least, whichever of these terms is the largest. And so if the bottleneck is the server upload, and it only needs to upload once, that's going to be the server's component. If the bottleneck is the download of the slowest client, that's going to be the slowest client contribution. And if the bottleneck is the aggregate, which is typically not the case, for uploading into the network by the whole peer-to-peer network, then it's going to be this third term, NF, the total amount of data, divided by the aggregate upload bandwidth. Okay. And so this term increases linearly with N. But what we find as you increase the number of peers, we notice that this term, the denominator, gets larger and larger and larger, which means that this term gets smaller. Okay, so let's take a look at an example graph, and this is in the book. We have a client upload rate of U, regardless of what U is, and let's assume F divided by U, file to go over one link for a client, is 1 hour, and the server is 10 times the client rate. So in this case, if the server is 10 times the client rate, well, the server is probably very likely not to be the bottleneck link. And dmin is at least U sub S. Okay, so in this graph, on the horizontal axis, we have the number of peers in the network. On the vertical axis, we have the minimum distribution time. The black line is the client-server approach, and we notice that this client-server approach is linear. As you increase the number of peers, commensurately, we get a unit step increase in the distribution time, and it keeps going up and up and up and up as you add more peers. Now, that kind of makes sense, because as you add more peers, more copies of that file have to be distributed between the server and each of those peers. But in the peer-to-peer network, we know that that file F comes from multiple locations. It can come from the server, or it can come from each one of those peer instances. And so as we increase the number of peers and in the network, while this minimum distribution time increases, well, you'll notice it turns the corner, turns the curve, and it kind of looks like it's approaching an asymptote. And this is because of that self-scalability property associated with peers. Each peer brings capacity to the network, and in this case, it brings the ability to distribute this file, thus acting like an additional instance of a server. And so this savings, you'll notice there's a big gap For example, the further we go out to the right, for example, for 20 peers, we notice that there's a huge gap between the minimum distribution time of the client-server approach versus peer-to-peer. So peer-to-peer is about 0.56 or 0.57, and client-server is 2 distribution time. So we get a huge savings. It scales much, much more elegantly when we use the peer-to-peer approach. And so let's take a look more intently at BitTorrent. BitTorrent is a peer-to-peer file distribution protocol, and in this, a file is divided up into standard 256 kilobit chunks. And each one of the peers in the torrent are going to exchange these chunks, these 256 kilobit chunks. They're going to send and receive them to one another. And so when they're receiving, they're acting like clients. When they're sending, they're acting like servers. The servers respond to the requests and send their chunks. And so we have an entity in BitTorrent called a tracker. And the tracker kind of acts like a phone book, a directory service. And when someone first joins the network, let's say Alice, a user, she connects to the tracker, and this tracker obtains a list of peers that are participating in this BitTorrent system. Now, of course, you wonder, how did that tracker know what the peers are? Well, when a peer wakes up and joins this peer-to-peer network, this exchange of chunks of files, they register themselves with this directory service. And so every subsequent joiner to the network contacts the directory service and gets the identifying information, the address, so that they can contact peers participating in the torrent. And so a torrent is nothing more than a group of peers that exchange these 256 kilobit chunks of files. Now, in aggregate, if each of them is exchanging 256-bit chunks of files, then in aggregate, by downloading these chunks, different chunks, from a large number of peers across the network, in aggregate, that's going to result in a very high performance transfer of the file or distribution of the file. And so Alice then, once she gets a list of peers from the tracker, she begins exchanging file chunks with other peers in the torrent. And so this exchange means that Alice can request chunks of files from peers, but Alice can also furnish chunks of files to others in the network. And so when a peer first joins a torrent, Alice first joins, she has no file chunks, but she accumulates them over time from a large number of other peers on the network. When peers start, they register with the tracker, and they get a list of peers, and then use that list of peers as the basis of connecting to some subset, and those subset we'll call the neighbors. And so you connect with not just any neighbors, but you connect with neighbors who prove valuable, and those that prove valuable are those that have chunks that you need in order to construct the file that you're trying to receive a copy of. And so while downloading, a peer also uploads chunks of files to other peers. And so peers may change who their neighbors are, i.e. who is better in exchanging, who's a better trading partner for them. And so peers also may come and go. They can leave the network whenever they want to, and then join the network whenever they want to. And that's called peer churn. And so once a peer then has an entire file, it may continue to participate and act as a source of chunks of that file to others, or it can selfishly leave and just say, okay, I'm just gonna have the file I need. I'm just gonna shut down and not participate. And so what happens when you request chunks? At any given time, different peers have addressing information and can connect to different subsets of the torrent, and they have different subsets of file chunks. And so a peer doesn't necessarily all the time have the entire file. You might have parts of it. And so periodically, Alice then will ask each peer for a list of chunks that they have. And Alice then uses that list to request from her neighbors all of those chunks that she does not currently possess. Now, of course, the scheme in BitTorrent is to request, or prefer to request first, those chunks that are the rarest, that they don't exist in very many places. Because you get a list of chunks from your peers, you know which chunks are in abundance, are on a lot of peers, or are very scarce, meaning only a small number of peers have that chunk. And so Alice engages in sending chunks, so-called tit-for-tat, and she sends chunks to those 4 peers that represent her best trading partners, those that are sending her chunks at the highest rate. So she says, okay, well, you're being beneficial to me, sending a lot of data to me at a high rate, chunks that I need, so I'm going to send chunks to you as well. And those peers that are not her best trading partners, so to speak, they're choked by Alice. They're choked off. They're not receiving and don't receive chunks from her. So Alice only gives chunks to those who are providing chunks to her. And then every so often, every 10 seconds, Alice reevaluates who her best trading partners are, who has the most chunks that she's been downloading, the most data that she's been receiving. In addition, Alice does the following, and this is an example of what's called the trade-off between exploration and exploitation. Now, exploitation is the maximizing of an action based on information you have, and exploration is a random guess in attempt to try to find something that's better. And so when Alice chokes off those who are not good trading partners and reevaluates and selects the top 4, she's doing exploitation. She wants to maximize on receiving file chunks as quickly as possible. And so she's always saying, are you still the best trading partner? Do you still have more chunks for me that I do not possess? But she chokes off those who are not the top 4. But at the same time, she gives others a chance that might not be the best trading partners. So every 30 seconds, Alice does this exploration. Every 30 seconds, she randomly selects another peer and then starts sending chunks to that peer. And the hope is that maybe she might stumble upon a peer that could eventually become a better trading partner than her top trading partners. And so every 30 seconds, she optimistically unchokes another peer, and the hope is that this newly chosen peer may join the top 4, because you never know. So you could say that Alice knows jiu-jitsu. She's choking and optimistically unchoking her peers. So let's take a look at BitTorrent's tit-for-tat. We'll visualize this. Here we have Alice, and here we have Bob. So Alice optimistically unchokes Bob. She randomly selects Bob as a potential trading partner, even though he's not among the top 4 trading partners of Alice at the moment. So then Alice starts sending chunks to Bob, and Alice becomes one of Bob's top 4 chunk providers, a good trading partner, and Bob starts reciprocating. Says, okay, well, let me start sending more chunks to you. Bob then becomes one of Alice's top 4 chunk providers, a good trading partner for Alice, and now Bob is in the top 4 from Alice's perspective. And so when you have a higher upload rate, you've found a better trading partner, and therefore you've gotten chunks of that file even faster. And that's the goal, is fast file distribution. So let's take a look at this video. And that video talks about BitTorrent, and we'll take a look at it briefly.
Our computer files aren't like they used to be. These days, a short HD video can be over a gigabyte in size. That's huge. The problem is that the bigger they are, the harder they are to share. Thankfully, we have options that make sharing big files over the internet fast and easy. This is BitTorrent Explained. Blake was so excited. He's the president of his local Sasquatch fan club and recently heard that a new video was circulating. He couldn't rest until he had that video on his computer. He tried to download it from the original website, but it was painfully slow. Because so many fans were trying to download it at the same time, the website crashed. He was discouraged. Then, a fellow fan said the video could also be downloaded via BitTorrent. She said that unlike typical downloads, files using BitTorrent actually download faster when more people are involved. and it works with any kind of file. To see for himself, Blake downloaded uTorrent, the world's most popular BitTorrent app, from uTorrent.com. He opened the program and was a little confused. There were no videos, and he wasn't sure where to start. But soon he realized that's because BitTorrent is a little like a web browser. Just like a browser needs websites to be useful, BitTorrent needs special files called torrents to work. A quick web search pointed him to websites with torrents galore. Soon enough, he found the Sasquatch video torrent, downloaded the torrent file to his computer, and with a simple click, uTorrent immediately sprang to action and the file started downloading. He could see it was working and wondered how. Later, his friend made it clear by talking about how downloads typically work without BitTorrent. When someone downloads a file, it comes to their computer in a stream from a single source. When multiple people want the file, that single source can get overworked and can even shut down. BitTorrent solves this problem by making each downloader a source. This way, they get pieces of the file, but also provide pieces to each other. Together, the downloaders become a network of multiple sources, all working to provide pieces to one another. This makes downloads fast and reliable. A couple of things behind the scenes make it happen. First, when he clicked download, Blake received a torrent file. This file has all the information about the video file, like what pieces are needed to complete it. But something is missing. Blake needs a way to connect to other users who have the pieces he needs for his file. BitTorrent uses a computer called a tracker that helps Blake's computer find other computers called peers. The tracker keeps track of computers that are downloading or already have the whole file and introduces Blake's computer to them. With the connections in place, he receives what he needs and also distributes pieces to others who are also downloading. Blake got it. BitTorrent works because it turns downloaders into sources, and more downloaders means more sources and faster downloads. In the end, Blake's video downloaded in no time at all, but he was a little disappointed. What he thought was a Sasquatch was only a Wookiee. But at least he now knows with uTorrent, there's a faster, easier way to download files from the internet.
Okay, so that's a little bit about BitTorrent. So now we'll turn our attention to content distribution networks. Now, video traffic is a major bandwidth hog for internet bandwidth. And Netflix, at the publishing of this book, comprised about 37% of internet traffic, and YouTube about 16% in residential markets or residential networks. And so there are billions of YouTube users, and at least contemporaries in contemporary times, hundreds of millions of Netflix users. It's only about 75 million at the publishing of this book, but nonetheless, one of the challenges we have is how do you get this video traffic, this video data to scale? How do you get to reach all these people? Now, of course, it's a mistake if you had a single mega server to push out all this data. And the challenge, in addition, is heterogeneity. Some people have set-top boxes, some people have mobile devices, some people have computers, laptops, what have you, that are all getting this challenge. They have different computational ability, different memory, and the bandwidth for the network that they use to gain access is different. It can be bandwidth, can be poor, or it can be quite fast. And so the solution adopted for this is a distributed application level infrastructure, so-called content distribution networks. And so video is encoded in a way that you can represent the same video, carry the same information at different resolutions so that you can now take advantage of whether you have a lot of bandwidth or you don't have much bandwidth. And so video is nothing more than a set of images at some frame rate, typically roughly 24 to 30 frames per second. A digital image is nothing more than an array of pixels, and these subsequent arrays of pixels are displayed to give you your video. And so when you represent video for streaming, there are two different ways you can represent it. And you do this because you want to try to minimize the number of bits that the video takes up in order to get good, fast video to you using up as small bandwidth as possible. And so there are two flavors of coding that you can use to represent the information content in an image and in a video. One is called spatial coding and the other is temporal coding. And with the spatial coding, what you're doing is if you have a set of pixels that have the same value over some span, instead of sending all those pixels, you have two numbers, one for the color of the pixel and the other for the number of instances or occurrences of that pixel. And so here in this top image, we have a number of pixels that are all purple. And these purple pixels, it makes no sense to send each one of these pixels over the wire. You count how many purple pixels you have in some succession, and then you say, okay, if it's 10, I write 10 and color purple, and it will get reconstructed on the other endpoint much more cheaply using up lower bandwidth than sending all 10 of those purple pixels. Now, the other approach is so-called temporal coding, and in temporal coding, when you have two images, certain parts of the image will stay the same from one time instant to the next. And so if you're doing that from one frame to the next, rather than send both frames, just send the differences between the frames from some time instant I to some time instant I plus 1. By only sending the differences, you're only updating parts of what that current picture is, and you're sending much less data across the network, because if your frame rate is fast, 24 frames a second, that's 1/24 seconds, you're going to have parts of your image change. And because that's such a small amount of time, not that much in your image is going to change from one instant to the next. And so therefore the result is that you end up sending less data across the network to represent the motion going on in that image. Okay. And so there are two ways of coding your video. One's called constant bit rate. That's a video encoding for a fixed rate. And one's called variable bit rate. And this video coding rate can change. And so the amount of spatial and temporal phenomena that you're coding is going to be variable. And so take, for example, when you encode a pixel, instead of encoding a whole pixel and the actual value, maybe you're taking a range of values of color and just calling that purple. And so you're not representing fine resolution, and you can also represent on through very, very high resolution when you're doing variable bit rate coding. And so this variable bit rate coding is trying to further minimize the amount of bandwidth or use full bandwidth possible in representing all the minute details in your video. And so there are different coding standards, the so-called MPEG standards, and the different standards correspond to certain densities or bit rates or levels of resolution. And so the simple scenario is you make a client request in the home, like you go to netflix.com and select a movie from your account. You contact a video server on which the video is stored, and then it streams or sends the frames of this video in time across the internet from the origin server back to the client. And so DASH, which stands for Dynamic Adaptive Streaming over HTTP, piggybacks on HTTP, and it's a protocol and approach for doing video streaming. And it's the prominent or the flavors or variations on Dash is the predominant approach for doing multimedia streaming over the internet. And so in Dash, the server divides each video file into a set of chunks, and each chunk is stored and encoded at different rates. And so that means that you can now fetch video based on some block of time, but this representation could be either very low resolution, low definition, or very high definition, and Dash can select from among them based on the prevailing bandwidth in that link from the origin server, getting that content back to the client. And so Dash also includes a so-called manifest file, and this manifest provides URLs for the different chunks, and these URLs locate, okay, the first chunk, the second chunk, the third chunk, but there are also different versions of the chunk. There's a first chunk, second chunk, third chunk in high resolution, first, second, third chunk in medium, first, second, third chunk in low resolution, for example. And so now the client is where all of the intelligence or the load is implemented or taken on. The client then, in your browser, periodically measures the server to client bandwidth. It measures how many bits it's getting per unit time, and based on this bandwidth, it looks up the inside of the information within the manifest, and it requests from that manifest one of those URLs to get these chunks one at a time. And now, based on this bandwidth measurement, the client then adjusts and can either choose between a high resolution, medium resolution, or low resolution version of that same chunk based on the available bandwidth measurement that it perceives. And so the client chooses the maximum coding rate that is possible or sustainable given the current measured bandwidth. And it can switch while the video is streaming. And so if you've ever watched something like a YouTube video or Netflix video, you'll notice sometimes if there's issues with bandwidth on your network that the video will start to get a little bit less definition. Maybe it'll get blurry, or maybe it'll be low resolution, and then it'll switch back to higher resolution. That's Dash in action, choosing between the different resolution versions of that chunk as it's requesting chunks over time as a result of feedback, i.e. that server-to-client bandwidth measurement. And so for Dash, all of the intelligence is put at the client, and that implements scalability. Because why have the server do this? You should charge the cost of all of this calculation and decision-making to the client machine. And that allows you to make your servers, or keep your servers, very or more so scalable. And so what does the client decisions have to be? The client needs to decide when to request a chunk. And because you're not just requesting the chunk as you need to display them, you're going to prefetch these chunks and buffer them at the client. Just in case there's disruption to the bandwidth, you can take those chunks out of your local buffer instead of from the server. And so you can imagine now we have a server on one side of the internet, and here's your client on the other side. Your client has a buffer, and then your client is getting these chunks from the server by consulting the manifest, and the client is then placing these chunks in its buffer, and when you stream video to the screen that you're watching, that video is coming out of the buffer. So when the client requests these chunks from the server, it requests them, prefetching them as it were, because if you're showing the chunk that you currently get, well, if some disruption happens to your bandwidth, the video is going to be interrupted. And so the client then decides when to request a chunk so that you don't get starvation of this buffer or you don't get overflow of that buffer. And that buffering is in place to try to alleviate issues that might happen with disruptions to your bandwidth. And so the client also decides what encoding rate to request. You get a higher definition or higher quality when more bandwidth is available, and then it can now switch to a different chunk associated with lower quality when the bandwidth is starting to decline. And it also selects where to request the chunk. Now, these URLs can exist in plurality for different locations. And so that client, when it requests it, might have one URL for server 1, another URL in that manifest file for server 2. And so not only can the client select from server 1 the next chunk, in addition to the quality or the resolution for the chunk, it can also switch to another server from which it's fetching the same chunks. And so that adds in a sense of redundancy and fault tolerance. Should something happen to that connection to server instance 1, it can always switch to another server instance, and that could be because that connection is broken, or if the bandwidth has degraded beyond a certain point, it might just choose to switch to a different server instance, perhaps in a different data center. So the challenge then is how to stream the content if you have millions of videos, lots of them, to hundreds of thousands of simultaneous users. And so we said that you could have a single mega server, and that's not a real solution. You have a single point of failure, you get a lot of network congestion because of the access link to the server. If you have a long path from the client to the server, you're going to potentially have some issues, right? You're pushing a lot of data over long distances, and if you can reduce the distance of which you push that data, you're going to get better throughput, better end-to-end bandwidth. And so you also have multiple copies of video sending out an outgoing link. And so the server then is pushing this out. If you have a mega server, you want to try to place multiple copies of your content closer to the access network for the different clients that are going to access it. And so the second option then is to take multiple copies of your content and push them into multiple geographic locations. And so if you're Netflix, you put copies of it in a data center on the West Coast, on the East Coast, the approaches people use. One is called enter deep, where you take these content delivery network servers, those that store those instances of video, their origin servers, you push them deep into the different access networks. And so there are companies that use this approach. Akamai is a very famous one that does that. And the idea is to put this content close to the users, because if it's close to the users, that bandwidth for accessing is going to be relatively large. And the other is called bring home, and that takes an opposite approach where you put the content delivery network servers in the points of presence. These are those facilities where different ISPs exchange data. So they're not within the access networks, but they're at those points at the seams where two different ISPs exchange data. Now, the CDN stores copies of content at so-called CDN nodes, and for example, Netflix might store copies of a movie like Mad Men in different locations. And so here we have Netflix, and Netflix might store, and this is the deep version, it might store copies of Mad Men in CDN server node instances inside of the various access networks. And so when somebody is requesting a video, you're in your home on your ISP's access network, you ask, where's Mad Men, push this request to the Netflix server, it returns back as a result the manifest file. Your client then accesses the manifest file and it directs it to a particular CDN node instance, and then it requests that particular resource using that URL for that particular chunk, the first few chunks filling its buffer from that local content delivery node, and then you stream the movie and you can watch your movie. And so now you can choose a different copy. Let's say there's some congestion that occurs in that connection between you and that server instance that's streaming the video. All of a sudden, it detects that the bandwidth is failing, and so the streaming client makes the decision to choose a different CDN node instance in another data center, and now the streaming continues without issues of bandwidth because it's a different path across the network. And so this over-the-top view talks about the network of these CDN node instances. And so the internet host-to-host communication, you can think of it as a service, and it's the manifest and the interaction of the client with the manifest along with its measurements that is a type of service it uses to select different particular CDN node instances with which to communicate and from whom to get these chunks, which are those parts of the video that you're streaming. Okay, and so these challenges in dealing with a congested internet, you have a bunch of questions you have to address. From which CDN node are you going to retrieve the content? So you're going to have to make that calculation based on what you perceive, you the client, as that measured bandwidth as you're getting the data. You also have to look at viewer behavior in the presence of congestion. So if you're getting congestion, all right, well, you might select a lower resolution version of that movie and fetch those low res chunks from the content delivery node, network node, from which you're currently getting your data. Now, of course, so the viewer might change the channel. So what do? It's also dependent on the viewer's behavior. Maybe the viewer decides to pause or to fast forward for the movie. What do? It's dependent also on that viewer behavior. And the other question that has to be answered, if you're the service provider, if you're Netflix, what content do you place in which CDN node? And that's a function of what pattern of accesses to content are you viewing over time for certain parts of the network. Okay, so let's take a look at the access. And let's say Bob goes to netcinema.com, that's the service provider, kind of like Netflix, and fetches a particular movie or video that is identified by this hash code. And so let's assume the video is physically stored in kingcontentdeliverynode.com, and this is the hash code here. It's netc6y ampersand b23b. Now that's the same as the hash code that we saw originally. And so this hash code means something, but here the important part to note is that this particular video is on King CDN. and that's the particular node instance, CDN node instance, where the content is found. So Bob goes to netcinema.com, and Bob then gets URL for the video that he wants to watch from the netcinema.com webpage. So now Bob needs to resolve netcinema.com hostname and goes to his local DNS to get the IP address for that. Now, given this netcinema.com, Bob's local DNS server goes to netcinema.com's DNS and gets back a URL for King CDN. Now, this is using a canonical name, and using this canonical name record, Bob then gets the IP address for the URL for King CDN. So then Bob takes this King CDN and then contacts King CDN's authoritative DNS server, specifies that URL, gets back the IP address. And so now Bob's local DNS server returns that DNS query IP address back to Bob, and then Bob knows to contact directly that King CDN instance and request the video and starts to stream. And so here we have a number of rounds. First, you have the request, and given that request, you resolve the address using DNS query. You get the IP address after using this canonical record to find the particular server instance that Bob's DNS server now needs to resolve as a name to IP address mapping. And so the first step is to look up that address from netcinema.com, and netcinema says, well, given that URL, there's a canonical name for it. This is the canonical name. Now Bob takes that canonical name, goes to the authoritative for that canonical name, gets back the IP address for the instance. Once Bob has that instance IP address for kingcdn.com, actually fetches that video he needs and then starts watching the video. And so a case study, Netflix, and Netflix, whether you knew it or not, uses Amazon Cloud Services, Amazon AWS, to run their whole CDN and network and video delivery service. And so they have a quite sophisticated approach, and if you want to learn more about the details, they do publish some information, but not all, but you'd have to get a job at Netflix to know specifically what they're doing. And so the first thing that happens, Bob has an account on Netflix, and Bob then browses Netflix videos. When you browse Netflix videos, you're actually browsing some listings in a server running on the Amazon cloud. So now you request a video. Now when you request a video, you get a manifest file for that video. And now that you have the manifest file, you then interact with that manifest, your client does, using Dash in order to stream your video. Before that, Amazon has uploaded copies, different versions of multiple copies of that video on different CDN server instances. And so when you interact with a particular CDN instance, this manifest has URLs that access this movie on different instances that your client can then switch between. So you might be accessing those chunks of video data from that first instance, you might switch to the second instance, or switch to some number of instances, and that's all driven by this manifest file, which is pre-populated based on those locations where Amazon knows it has uploaded versions of that movie across the different CDN nodes on the network. Okay, so with that, that's all I had for today. And as usual, please stay healthy, stay safe, and I'll see you all on Thursday.